Okay, so this is basically the second video of the course Introduction of Journal Bearing. Frankly speaking, it was some unrecorded portion of the first video, but I don't know why it has not been recorded. Maybe my disk space was very low, so that's why the portion has been not, it has automatically stopped after a certain slide. So, uh, basically, this to understand the hydrodynamic bearing operation, I have given this example, which is basically the aquaplaning. So, what is happening basically uh, in case of this hydrodynamic bearing? See, the liquid, due to viscosity of the lubricant, the liquid which is just along the circumference or the periphery, or whatever you tell, circumference of the this journal, this will have the higher velocity. Hence this area will experience lower pressure, static head, and this area, your approximately from that Newton experiment, what we conceptualize, the inner lining of the babbitt or the bearing shell, that will be at rest. So there, the comparatively the static pressure will be high. So this will create one lifting force, which will be basically floating the shaft or the journal inside the shell. Okay, so hope this basic mechanism you have understood. So in the subsequent lecture, I will show you some practical example with the help of this bearing chart. There you have to calculate the Sommerfeld number, and from there how to decide this minimum gap, means what should be the minimum clearance between the bearing and the journal. Then what how to decide the maximum operating temperature of the mm, uh, liquid or the lubricant. Okay, and the size and everything. Okay, that I will, with some practical example I will take, and from there I will show you the derivation. And this video mainly I want to show you the utility of CFD analysis to very quickly design the mm, bearing with some thumb rule. Okay, so which will be suitable, what kind of geometry of the sleeve or the bearing will be suitable to handle a particular load, how the dynamic capacity of the bearing is varying based on the um, geometry of the bearing, all these things. So here just I want to show you this report. This I means the analysis output, this I've done long back. Here I have taken totally 8 configurations. So the first one is the uh, uh, cylindrical or the spherical cylindrical configuration. Here this black color portion, it is basically the journal or the shaft, and the in between the white color portion, it is the liquid or the lubricant, and the outer this red color portion is the uh, bearing. Okay, so with this 8 config, and the second one is the, you see the your bearing shell size is elliptical, and the third geometry, basically it is the basically the cylindrical configuration, but slightly it is these two halves are slightly displaced, splitted halves. Okay, so and the fourth one, this is the uh, elliptical type, but the there is some these two halves are, there are two lobes, there is a gap in between. You can consider that is the oil groove or the lubricant groove or whatever you may tell. So the top one is one lobe, and the bottom one is one lobe, and the fifth one, that is three lobe, you see. So these are the three lobes. Okay. And sixth one also three lobes, but what is happening, you see, this geometry is just rotated 45 degree. So in this case, the load is completely, during the rest, the load is completely sitting on one pad. But as this is rotated 45 degree, so you see, this is the oil groove. So the load will be sitting in two lobes. Means load will be in between the pad. The seventh one, this is, you see, there are four lobes are there. In this case also, the say this is the fourth pad. So the load will be completely sitting on the fourth pad. In the eighth configuration, this is again 45 degree rotated. Okay. And there, you see, the load will be sitting between this pad and this pad. So basically LBP means, I mean to say, the load between two pads. LOP means load on the pad, like that only I mentioned. And this can be simulated very easily, hmm, very easily to understand the behavior. You see, in the last case, this is the four lobe where the load is sitting between the pads. There, the upward thrust means the upward lift, it is maximum. This bar chart showing this started from 0 to 14 bar. See here, it is the pressure is around 14 bar. So if it is 14 bar, and you can imagine if the surface area, so how much thrust it will be, so much, this dynamic capacity will be so much. So without going to detail calculations and experiment, you can conceptually, using this kind of readily available tool of CFD, you can very quickly understand how far your design is correct and all. This all simulation and everything I will show you in step by step. So you might have seen the people who are handling with vertical centrifugal pump. So the very near to the impeller, there will be this kind of journal bearing, which is basically hydrostatic bearing. In case of hydrostatic bearing, the instead of the liquid pressure, means the oil film is forming by its own. In case of hydrostatic bearing, the external pump or external some mechanism, some separate mechanism is attached with that, mm, uh, uh, which will create the pressurized flow, and that flow will lift the shaft. Okay, this is the means in starting itself, before starting the, if, or but it, you can tell the forced mechanism to lift the shaft. So in case of this large scale vertical coolant pump, you might have seen the very near to the impeller there will be a hydrostatic bearing. Means while the liquid is coming out through the discharge, there is some hole. So due to discharge pressure itself, some portion of the liquid through the hole, it will coming to the bearing area, and it is creating the lift force. This can take the radial load. And the top of the pump, there will be the thrust pad, and in between there will be the liquid, which is basically operating as hydrodynamic bearing, the operation which I have explained here. And you might have seen, interestingly, the coupling between the prime mover or the motor and the pump, it is not a rigid coupling, it's a um, flexible coupling, because the motor is not designed to handle that full inertia. means along with motor having one inertia, along with that pump inertial that load is there. So that is, we have to then the bearing, if it is a rigid coupling, then the motor top non-driving and thrust bearing design will be, means the capacity should be very high. So to avoid this reason, the coupling will be in, because as there will be slightly leap when the oil film is generated. So the coupling between the prime mover and the pump is flexible coupling. Okay, and that load is taken care by pump top side thrust pad. So these all these things, specific things we will learn slowly, and that time we will understand how this CFD is crucial or very efficient tool to conceptualize this all about the design. So thank you so much. I hope you learned something. Thanks for your patience.